Thank you, Professor. So hi everyone. I'm Xiao from Shanghai Jiaotong University, and I'm very pleased to present our work published in the CAD journal. So this is the title, Professor Wang just mentioned it. First of all, about the background of this work. So the structures that we study are the spherical jointed structures. So they consist of cylindrical bars connected by bolts, usually arranged in specific patterns, and they're widely used in architecture, such like the lattice roofs or some mechanical parts, especially when additive manufacturing and more recently the metal materials. So because of their excellent mechanical properties and lightweight characteristics. Okay. So the original motivation of our work was actually from the health monitoring of existing laboratories. Okay. So during the launch of this period of the structures, the geometries of the lattice roof may change slightly, but even small geometry changes will cause the node cap bearing capacity to change and even to structural safety failure. So we would like to analyze the structural performance of these lattice roofs. But before that, we need an accurate CAD models. But usually, CAD models are often unavailable for early built lattice structures. Even when drawings are available, the resulting CAD models usually only represent as-designed geometries, not the as-built or as-is conditions. So they will not reflect the current state of the structures in service. So under this background, we would like to reconstruct the CAD models directly from the point cloud data. But actually, there are quite a lot of point cloud reconstruction methods developed. So our goal is to find a way that can be robust, robustly reconstruct the CAD models of this particular lattice structures. Okay. So the first stage of our method is the plane fixing of the point cloud. So here I give you the 2D example for expression. So for this 2D plane sets, we would like to find a set of planes that best fits this plane set. So during the plane fixing, we would like to find, for example, for this plane sets. So the three planes are the basic fit to this plane set. So during the plane fixing, we have two control parameters. So one is the approximation tolerance, and the other is the smaller size. And during the fixing process, the outliers will also be excluded. So the plane fixing should satisfy four requirements. First is the fidelity, meaning that planes should fit the points well. Right? So for example here, so the three planes here do not fit the point well. And the second is simplicity, meaning that actually we do not want a point sets to be approximated by one single plane, be split into several parts. So the third is completeness. That is for all the points that fall within the approximation tolerance that are all included in the fitting process. And the fourth is regularity. So we need to add some regularity constraints to the fitting process so that the orientations of the planes have a consistent constraints. Okay. So to satisfy all the four requirements, we formulate an energy function. So this energy function includes four terms, and each term corresponds to one requirement. After minimizing this energy function, we are going to plane region that balances the fidelity, density, completeness, and regularity. So next, I will briefly explain the four terms. The first term, the fidelity term, actually will measure the distances between the points and the fitted planes, normalized by the fitted tolerance. So if we have a smaller value of this term, so it means that the fitting quality is better. And for the simplicity term, we actually measure the ratio between the number of fitting planes and the upper bound. So the upper bound of the fitting planes can be estimated in that because each plane, we assume that each plane contains only at least prescribed minimum number of planes. So this upper bound can be estimated. So the term is completeness term. So we simply just calculate how many points not included fitting process. And like that. So actually we would like, for example, for the cylindrical surfaces, we would like the planes fitted to this cylindrical surface to be parallel to a planar. So we add this additional constraint to this function. So this is the importance of the energy function. So after optimization, okay, we will get an optimized plane fitting in point house. And the points are assigned to corresponding planes. So after we get the optimized planes, each point will be projected to the corresponding plane, and we can construct planar convex house according to the projected points. And this figure shows the planar configuration of the convex house. So for the initial planar configuration, you can see that actually the convex house overlap considerably. But after optimization, the convex house will have a better distribution. So next will detect primitives and reconstruct the CAD models based on this convex house. So let's how to optimize the plane or how to get a better convex house. So actually we want to optimize or minimize energy function. So what we do is that we define 5 local geometric operators. So these 5 geometric operators are first the transfer operator, which actually to exchange the points belonging to neighboring planes. And we also have merge operator, which actually merge 2 planes into 1 plane. And split operator just splits 1 plane into 2. And exclude operator, which is to exclude points that lie far away from the fitted planes. And also with insert operator, which is to include the the outliers at the current state included in the fitting process. So these 5 operators will be iteratively applied to the energy function until the energy function converges to minimum. So you will see that after optimization, the convex house will actually represent planar configuration is much better distributed. So this is an animation of this optimization process. So in our implementation, we started the optimization for the initial planar configuration with the region drawing method. So actually we initialize the planar configuration with the region drawing method, and starting from this initial planar configuration, we optimize the energy function to get the optimized planar configuration. So and we get convex house, the discrete convex house. We start the primitive section that's on this convex house. So we first do this. So we first need to create the neighborhood relationships around this convex house. So how to do it? So for a given convex house, example here, for a given convex house, so its neighbor house are those that are closest to at least one of these vertices. So for each vertex, we can find a neighbor house. So to accelerate this process, we actually build an ADB tree containing all the edges of the house. So for each vertex of the house, we find the nearest edge belonging to another convex house, and this convex house is marked as a neighbor. And after all the vertices of the given convex house are considered, and then all the one-way neighbors of this house will be found. Convex house often has the neighborhood relationship around the convex house. So actually this blueprint or the segmentation of the convex house is based on included angle between the normal directions of two neighboring convex houses. If the angle is below a specified threshold, the two houses are considered to be in one group. So this segmentation of convex house is completed when every convex house is assigned to a group. So this shows the convex house segment result. So the middle figure is the convex house obtained after the optimization, okay? And then we can do this segmentation so that we can segment the convex house into different parts. For each group of the convex house, we need to identify whether it represents a cylinder or a sphere. So this actually becomes a quite easy problem. So we can actually use the principle of component analysis of the normals of the convex house. So the normals of a sphere, the principal component analysis would be three significant non-zero eigenvalues. So for cylinder, it would be two eigenvalues. So this will help us to distinguish whether this group of convex house represents a sphere or a cylinder. After we classify the group of convex house as cylinder or sphere, we can approximate the geometric parameters of cylinders or spheres using the square splitting. So that is the headline of the entire reconstruction process. So in our implementation, before we generate the convex house or before we do the plane making process, we actually have a pre-processing which is to cluster our house. So that we can do the plane to each set of the points independently and in parallel. And this will significantly improve the efficiency of the reconstruction process. So this is the overview of this method. So let me show you some results. So the first example is a Bonino lattice. So this lattice contains a intersecting box, spheres, and intersecting cylinders, okay, which is a bit challenging to distinguish the two spheres or the two cylinders. But our method is consistent for reconstruct modern spheres and cylinders. We verify or test our method and using the model from the same. And of course, the thing I can do the same doesn't provide the data structure and the point cloud directly. We actually discretize the models provided in the data sets to get the mesh and then to create the lattices ourselves, and then also to create the point data sets ourselves. And so this point data, it has very complexity and also varying scales, and our method exists quite robust to reconstruct the lattice structures from this point cloud data. So we take the robustness and accuracy of our method. So since actually in real scale data, it is inevitably concludes the frame data with scattering errors, right, and measurement errors. So we have to verify that our method is robust to noise. So in our study, there are two different types of noise data. One is a random noise, and the other is outliers. So as can be seen from the results, so our method is robust to moderate noise levels, but for quite high noise intensity, our method may give some unrealistic reconstruction results. But actually, in real scale data, this noise intensity may not occur in real scale applications. With fixing, for example, the feature effect, which is widely used in point cloud segmentation, and also two different vectors, pasnet and HPA, for this simple lattice units. But unfortunately, for this simple lattice units, the two different methods, the performance are quite poor. And for the efficient effect, it also gives incorrect segmentation for the overlap and BCC models, so which contains overlapping or intersecting spheres and more complicated connection in gimbals and bars. Then we would further compare our method with the construction methods. For example, the point to CAD, which is a deep learning method, and a variational method in fact. And to ensure a fair comparison, we actually provide same segmentation results to point to CAD, and to our methods. So here we only compare the reconstruction results. So after comparison, we find that our method is faster and also gives a more accurate reconstruction results than other two methods. And finally, we went from method to scaling method. Okay. So what we do, we actually pre-printed lattices. So we have a model, and then we create a lattice, the CAD model of the lattice, and then we print the lattice with a 3D printer. So this printed lattice, they have the surface defects, because the printers were printed in material layer by layer, so the surface is not smooth. And then we scan the lattice with a handheld scanner to get the point cloud data. And this point cloud data will contain like the scanning errors, and also it may contain some data loss because for some parts of the lattice we may not get the points of the scanner. So this is two examples of the 3D printed lattice. So as we see that our method can robustly reconstruct the CAD models of the 3D printed lattice, and we compared CAD models that we constructed and the original CAD models. And actually, the error is actually at the same level as the scanning accuracy. So which also improves that our method is robust and accurate. Okay, so that's the conclusion. So we adapt the robust space-based algorithm to consider the fidelity, simplicity, completeness, and regularization of the thinking process. And we use the planar convex house as an intermediate representation to segment the point cloud efficiently. And our method is robust to moderate noise intensity and more efficient than other methods for reconstruction of lattice structures. Okay. So that's my presentation. Thank you for your attention. Thank you.
So, so Xiaohu, um, one question, I saw like most of your data are actually synthesized um, from the traditional mesh, right? Uh, I'm not sure whether in real world application, do you have this kind of data that is purely just a sphere joined lattice? Do you have this kind of real world data?
Uh, and so actually, this data frame like simply containing cylinders like spheres, like pipeline, right? And in practical engineering, so usually we latitude. So if you go to stadium or some sports center or see bedrooms, that kind of bedroom is kind of latitudes. So they are typically consist of the spheres and cylinders. So in practical engineering, so if you want to get the CAD models of these structures, so we need to scan those rooms to get the data, the point data of the spheres and the cylinders.
Okay. Any questions from the audience? If not, let's thank the author of this paper for their presentation.
Thank you, President. Thank you, Secretary. For the proper
So this paper is uh, a structural analysis text to be used for the AI starting in the next process.
Yes. I think it's okay. Okay, thanks, Mr. Chairman. I'm going to present this joint work uh, with Italian colleagues. And here is my presentation outline. I'm going to start to recall some features of the paper and then talk about the context of assembly model. Then we will see the structure of this analysis we've conducted and talk about the geometric interfaces that we propose in this paper. That is going through the analysis of digital component catalogs and spatial distribution of interfaces, as well as the analysis of CAD assembly module operators. And I conclude. So some features of the paper and the relevance for several scientific topics that the component interfaces appear to be something that is efficient and multi-purpose entities for various applications related to the CAD environment. There are some formal definitions. That's a characteristic of the paper. There are many definitions in the paper, and that's what we've tried to really formalize as much as possible. And trying also to keep an eye on enlarging the range of interfaces and components that could be addressed through the paper, the scaling issue is something important. And we've considered the context of commercial CAD software, their capabilities, and also the context of company-based CAD assembly model. So this is relevant for assembly modeling processes, among other topics, as it is listed here. So talking about the assembly models, the regular context is that you can find assembly models on repositories, okay? GrabCAD or Imati repository. And then you have either mesh assembly model or CAD-based or step files that are also frequently available. Assemblies from companies are hardly available. That's a strong issue, and that's why we set up this work. And interfaces between the components are some key information that can be used later on, as I already discussed. So what we've been doing is to focus on geometric issues about interfaces. Still talking about assembly models, as you can see with this example, here we have a cutout of a hydraulic pump and several local zones. You have component shape variability that you can face in assemblies, like here with the white zone that is here, indeed a bearing, a ball bearing, and the ball bearing here it's a cutout also, but can be represented with its balls or just with nothing as a simple solid. Okay, so you have a very wide range of representation of components that you can face. You have also a wide variability in terms of interfaces. It's not only surface contact, even though it's a fewer number, but you can have, if we consider this example, so it's the dynamic seal of the pump here, and you have a Belleville washer that is indeed like a conic shape, and so the contact here is just a circular line. Okay, it's not a surface; it's a circular line in this case. So what you can face also is that still near the bearings here, so the brown areas that you can see here, around the elastic ring, you can see some distances, I would say, and the distances can be spread differently. And so that's also a type of question when you are handling these assemblies. And still about distances, for example, here with the nut stud configuration, you have this type of distance, 0.1 millimeter, but the question is that is it consistent or inconsistent? So how we could process that? So that's the type of question we find in handling assembly models. So the structure of the analysis we've performed is to say, because having access to industrial assemblies is very complicated, what we can do, since we know that on one side, of course, people in industry are using CAD assembly modules, okay, as you see here. Then we've been going through the fact that these CAD assembly modules have a set of operators, and we can structure these operators according to different sets. That's what we've been doing here. Okay, so the set of operators related to the relative location prescription of components, classically what the constraints that are specified to locate components with respect to each other, that's the L set, You have also another operator set that is related to the distribution of components, the spatial distribution of components, whether repetitive, linear constraints or rotational constraints like you have here for the screws. So that's a way to structure. So I'm going to talk about L and D operator sets. The other one I don't have enough time in the presentation to talk about. And so we have also component catalogs. Component catalogs is indeed what the industrial are going to use, because they are not trying to recreate components. Component providers are providing digital catalogs. And so we can start from that. And the digital catalogs, well, what we know is that the providers rely on standards in any case. Okay, so what we've been going through is to look at these digital component catalogs on one side, and also to look at the behavior of CAD assembly modules. And what we know is that because compared to repositories, in repositories, the model you find, you don't know whether the components respect some standards or not. You don't know whether the components in some standard, what can be considered standard components are coming effectively from digital catalogs or not. Okay, so you have question marks here, and you cannot, you don't know precisely what is somehow the quality of these models. Okay, so going through these inputs and analyzing these inputs is a way to get more information that can be considered as closer to what is the context of industrial people. So talking about geometric interfaces and how to define them, of course, we are going to, in the first step, distinguish what we've called principal faces. That's to say planar, cylindrical, conic, spherical, and toric surfaces, because they are related to the joints for most of them. And so they are directly connected to the interfaces we can face between components. That's one aspect. Then we consider, apart these principal faces, the secondary faces. You have an, sorry. You have an example here. So the primary face is a cylindrical one, but here the interaction or the interface between this plug screw and the casing here gives this type of volume, and here this free-form surface is indeed a secondary face. Okay, it's not a principal face as we have qualified it here. Then the interface, the definition is just the intersection between the component, but it's a non-regularized Boolean intersection. Okay, considering that as we can see, I mean, the intersection can lead to a surface, can lead to a volume, can lead to a curvilinear path or to a point. Okay, as we have examples here. And so we have structured this interface to consider the fact that the interface can be decomposed into elementary interfaces. Elementary interfaces, that's to say of one category, one manifold. So that's to say we have a decomposition according to the fact that we can have volume elementary interfaces, that's to say interference, as we have here. We can have surfaces, and surfaces can be with several partitions or non-path connected configuration. So that leads to different elementary interfaces. You can see here the two pink areas. If the elementary surfaces are connected, what makes a difference is the difference in terms of geometric parameters. Here we have an example with this tab washer that has a contact area here and a contact area here. So it's two planar contact, but not the same geometric parameters of the plane. And so it's two elementary interfaces. So yeah, you have also curvilinear and point. You have this example about curvilinear with the curvilinear contact between the ball here and the cylindrical part. And you have also point contact example between the sphere and the planar area here as an example, because it's an example of a simple working mechanism in a gearbox in this case. But you can have also more complex configuration of interfaces, like with gears and in assembly models, you can find this complex distribution of interfaces that we are going to talk about a bit later on. So it can be also non-manifold, indeed. You can construct, even though it's not mechanically very relevant, but you could construct this type of geometric configuration where you have a planar contact here, this planar area, and you have linear contact here, another linear contact here, okay, that is connected to the planar one. So it's really a manifold configuration in this case, and you can have a punctual one also. Okay, so that's the explanation, but the definition that we give to the interface. And so one part of the study is the fact that we've evaluated and analyzed CAD commercial assembly modules to see into which level of accuracy this type of interface can be reached. And we come up with this value as a relative error level, okay, that is common to most of the modules. So that's a reference value. Then going to the analysis of digital component catalogs, what we can see that you have, even though you have large, standard definition of components, you can still have a large variability in terms of shape. So here it's from different providers, the same standard, but as you can see, I mean, the driving area or the screw here, very significant weights. This is another standard. That's also a variability for the bearing. You have an example. What you can find also in digital component catalogs, the fact that for the tab washer, you never find the tab washer like that. You find the tab washer, I would say, in a rest configuration, because the tab washer, indeed, between the assembly phase and the working phase, is subjected to plastic deformation. Okay, and so the fact you have plastic deformation, of course, the shape is very different in the working phase and in the prior to the assembly phase. Okay. So that's what we can also highlight. But when we summarize some analysis of this digital component catalogs, what we find out is that indeed there is some invariant information, and the invariant information are the mounting requirements of a component. Okay, this is exemplified here with the screws, where the screws here, the plate P is really common to all the screws, independently of the manufacturer, the provider, independently of the standard, and so on. So this is really something that is a strong information, like the coaxiality with the thread for the other component, the nut part, say. Okay, and that's the same for the bearings. Okay, indeed, I mean, for the bearings, the mounting requirement you see here with the cylindrical area of the inner ring and outer ring, and also the planes here that can be used for the mounting requirements. So that is also something that is common independently of the other representation. But there is a large diversity of components, in fact, and that's really also a challenge, because you can find also some components in digital catalogs for metallic frames of windows and so on, like this type of component. And here the interface will be just a set of linear paths. Okay, so that also illustrates the wide diversity. Then talking about the special distribution of interfaces, what we came out with the CAD assembly modules is in fact the fact in CAD assembly modules you can prescribe the distribution in different ways. One way is to say when you have an angular configuration like this one, you can say n components and distributed over 2 pi, and the user either is saying prescribing the n components, and then the computer is going to evaluate the angle alpha, but it can be the other way also. And when people are doing the other way, sometimes they approximate, okay? And if they approximate this value as they want, okay, of course you have a round-off. So it can be considered and regarded as a minor approximation. But indeed, this minor approximation is going to have also an impact on the interface, okay, between the components. And so this is going to generate some noise in the model. And in the same way, what we can see also is that on the components themselves, this circular distribution can be also approximated. Okay, this is part of the modeling phase of the component. So these two approximations can interfere and add noise, so that the symmetry properties are somehow lost. Okay, and so what is appearing as something important is that the symmetry properties of components and the symmetry properties about the distribution should stay to be consistent in the same accuracy level as the one that is used to compute the interfaces. Okay, and we see also that inside the website of some suppliers of components, the symmetry properties are not necessarily satisfied at this accuracy. Here you have an example for this supplier where you have effectively the two symmetry planes, but for this one there is only one symmetry plane found. Okay. So the accuracy is not the same the moment among the suppliers. To try to reduce these constraints about the symmetry issues, we've seen that when you have some configuration with gears, very often, as we've seen before, the wheels have teeth that are interpenetrating. So we get a large number of small interferences, I would say. Here, what we propose is to introduce the notion of interface envelope. Okay, so this interface envelope is in fact the domain that you see here in orange, and which we have properties here within this domain where the line of action that is appearing here is the basis of the meshing process between the wheels, the gear, and so this line of action contains theoretically all the contacts. okay, that can reduce to line of contacts in case of helical or straight gears. And if there are interferences, indeed, all these interferences will lie inside this envelope. Okay, so you can use this concept of envelope to relax the constraint about the accuracy as it appears here. And so this envelope concept can be also extended to thread depending on the representation we have here. Okay. So finally, what we can see is that we propose definition to characterize what we call a nominal assembly representation. We focus on the LND operator sets. We've seen that the epsilon tolerance that is linked to the CAD assembly modules is something important. And what we are trying to address is to go towards the notion of closed world assumption that is derived from the formal system of logic, where we try to identify configurations that we can characterize as true, that are effectively true. And this is illustrated with the notion of consistency of interface and enable, for example, in this configuration to characterize the fact that because the interference here is not based on the coaxiality of the cylinders that is within the tolerance of the modeler, this is an inconsistent interference. And this is also important, this notion of accuracy in connection with the tolerancing phase an assembly. You have an example here of this tolerancing configuration, where for tolerancing the dimension, the height here are derived from the components themselves, their intrinsic dimensions. The interfaces, as we've seen, are obtained from the LND operator sets, and the epsilon I here that are the purpose of the tolerancing phase are influenced by the interfaces I and G. And so it's important indeed to have the tolerance of computation of the interfaces much smaller than epsilon I. So why? I mean, there is too much noise in computing the tolerance if we want to use this type of information. So this is also reinforcing the fact that the interfaces must be computed within this tolerance epsilon. Then the conclusion, we've seen the main point here regarding the notion of strong impact of component interfaces, the mounting requirements that are appear as invariants, the notion of interface envelopes that can relax some constraints, and there is still room for some complementary work. Of course, thank you for your attention.
We probably have time for one or two questions. So the questions from the audience.
Thank you for this very nice talk. So I know in the learning community they are trying to find out a nice way of defining CAD model that would be compatible with their with generative algorithms, like being able to produce valid CAD models using AI model. And I was wondering whether probably the answer is too early to know, but whether or not the analysis that you have pursued could be served as the basis of let's say parametric definition of valid assembly that they could input in their generative structure to produce a valid CAD assembly, which is what they are not doing at this time. They can produce sometimes CAD models, but not at the same
Yes, it's a good question. I think that this notion of consistency and the aspect of accuracy we've came across show that it can be effectively of interest to try to use, I don't know how, but to try to use this type of input to get models that would be say ready to use, consistent, more consistent, of course. Yes, yes. Thank you.
Thank you. Any further questions from the audience? If not, let's take the speaker again. Okay, the third paper of this session is of intersection detection algorithm of street surfaces based on geometric features of spine curves.
Afternoon, everyone. My name is Aizen Wang. Welcome to my presentation on self-interception detection algorithm of sweep surface. In modern CAD, what follows? Sweep surface play an important role in product design. Yet self-intersection analysis remains an open challenge. Due to this issue, we present an approach for detecting self-interceptions in parametric sweep surface generated by a planar profile along a planar span. My presentation is composed of 6 parts. First, I provide some background on the topic. Next, we introduce the definition of sweep surface, local self-intersection detection, and global self-intersection detection of sweep surface. Finally, examples are given to verify the effectiveness of the algorithm, and we present some conclusions on the topic. Computer-aided geometric modeling method often generate self-interceptions when module shapes, like reference surface, sweep surface, offset surface. Such self-interceptions not only damage the model's quality, but can also lead to unpredictable failure in subsequent operations, like geometric processing or unsafe test generation. Therefore, the reliable detection of self-interceptions are critical capability modern CAD systems with direct impact on machine verification and path planning. Importantly, exact sweep surface cannot make use existing nervous self-interception algorithm. Prior work has checked the special case, circular profile, type surface, and 2D closed profile generalized cylinder surface. No prior study has proposed an efficient method for self-interception detection in sweep surface, leaving a gap in CDCM workflows. To address these issues, we present a complete and accurate method for detecting self-interceptions in sweep surface generated by sweeping a planar profile along a planar path. We also classify self-interceptions into local and global types. For global self-interceptions, we further classify them into offset curve and offset stream cases. Mathematically, the parametric expression for sweep surface is defined by a planar profile curve and a spine curve as shown in equation 2, where the CFU is the spine curve. The CPV is the profile curve. RU is the rotation matrix dependent on the parameter U, thereby ensuring geometric orientation consistency. This figure shows the process of generating a sweep surface based on a profile curve and a span curve. In figure A, the red curve represents the span, while the blue curve denotes the profile. The green arrow indicates the tangent vector at the starting point of the span. Figure B shows the sweep surface generated under these conditions. It further shows the sweep surface generated when the span and the profile do not intersect in this figure. Self-intersection in sweep surface can be classified into two types: local self-intersections and the global self-intersections. Local self-intersections arise when the offset distance from a point on the profile curve exceeds the curved radius of the span curve, which is related to the span's local curve properties. The case 2 is global self-intersections, result from spatial proximity between the two distinct segments of the span curve, leading to self-overlapping of the sweep surface in 3D space. This algorithm gives the detection process for local self-intersection in sweep surface. It accurately identifies the presence of local self-intersections. The detection of local self-intersection in sweep surface is related to the curved properties of the span and the standard projection distance of the profile curve. This slide gives an example of a local self-intersection. By our algorithm, the local self-intersection point is detected on the sweep surface at the curvature extreme of the spectrum. This slide gives an example with two local self-intersections by our algorithm. Two local self-intersection points and are detected on the swept surface, one at each curvature extreme of the spectrum. Next, we present a detection algorithm for global self-intersection in sweep surface induced by single offset curves. The first detection framework integrates spherical curvature analysis with critical offset distance computation. For global self-intersection detection based on offset stripe self-intersections, it can be classified into two types, as shown in the figure. The case one is minimum distance in induced self-intersection caused by local distance minimum along the parameter curve. See figure A. The case two is underpod introduced self-intersection caused by underpod effect. See figure B. This figure shows the geometric representation of global self-intersection in offset strips. The gray area indicates the self-intersection regions of swept offset strip. Based on above analysis, we present the main result of our work, the algorithm framework for self-intersection detection of sweep surface specifically. The algorithm shows remarkable effectiveness in addressing local self-intersections, global self-intersections introduced by single offset curve, and the global self-intersections caused by offset strip. From this algorithm, we can see the input is one spectrum and one profile. The output is the self-intersection result. Next, we present some examples to show the effectiveness of the proposed algorithm in detecting self-intersections in sweep surface. In figure A, yellow points mark the curvature extreme of the spectrum. The red and cyan points mark the position corresponding to the maximum and minimum offset distance on the profile. Figure B shows the generated sweep surface. The proposed algorithm successfully detects local self-intersection regions on the sweep surface, marked by the red box in figure C. Figure D provides a section view of the surface, focusing only on the regions near the local self-intersections. As shown on the previous slide, the spectrum is a cubic nervous curve whose control wall matrix and node vector TS and US represented. The profile curve is a cubic B-spline curve whose control point matrix and node vector are DP and UP represented. This example shows a case of critical local self-intersection in a sweep surface. The spline curve has multiple curvature extra marked by the yellow part in figure A. But the local self-intersection is detected only at the first curvature extremal, as shown in figure B. The point corresponds to the minimum curvature value and the minimum offset distance. In this example, both the spectrum and the profile are cubic nervous curves, as shown on the previous slide, whose control point matrix node vector are ds, us, dp, and vp. This example shows the robustness of our algorithm in handling critical global self-intersection in spatial surface, which caused by the minimum distance of the span. Figure A shows the span in the profile curve, where the span curve has a pair minimum distance faults. Figure B, the green curve segment, the green curve represents the span offset curve with the maximum offset distance. Figure C presents the spectral result where a tangential critical global self-intersection point exists, which is also the only global self-intersection point. As shown on the previous slide, the red span curve is a cubic nervous curve with a symmetric shape, whose control point matrix and node vector are ds and us. The blue profile curve is a cubic p-spline curve whose control point matrix and node vector are dp, up. This example is present to show the global self-intersection in spatial surface, which is caused by underpart self-intersection of offset curves. As shown in figure A, the red span curve is a cubic B-spline. Figure B shows the green offset curve corresponding to the sine point with the offset distance corresponding to the minimum projection distance on the profile. In figure C, the red point marks a global self-intersection. As shown on the previous slide, the red spline curve is a cubic B-spline whose control point matrix and node vector are ds and us. The blue profile curve is a cubic nervous curve whose control point matrix and node vector are dp and up. This example shows the self-intersection of the offset strip caused by the minimum distance and the corresponding global self-intersection of spatial surface, as shown in figure A. The span curve is a cubic curve. Figure B shows the offset strip obtained by projecting the spatial surface on the xy plane. Further, we obtain the global self-intersection point on the spatial surface by our method, the red point in figure C. As shown on previous slide, the span curve is a cubic nervous curve whose control point matrix are ds and us. The profile curve whose control point matrix is dp. The profile curve is a cubic planar. This example shows the self-intersection on the offset strip and the corresponding global self-intersection spatial surface. As shown in figure A, the span curve is a cubic number. Figure B shows the offset strip and it can be observed that the offset strip has self-intersection induced by interpoles. Further, our algorithm is applied to calculate the intersection between the profile and the profile curve and the subpatch of the spatial surface. The red point in figure C marks a single global self-intersection. As shown on the previous slide, the span curve is cubic nervous curve whose control point matrix and node vector are ds and us. The profile curve is quadratic-Attraction Subdivision whose control point matrix is dp. This table provides a qualitative comparison highlighting the relative applicability, complexity, and the limitations of the three approaches. This shows our method achieve greater generality, and robustness. In the end, I give the conclusion of the presentation. We present an approach for detecting self-intersection in weak surface that address three types of self-intersections: local self-intersection, global self-intersection based on single offset, global self-intersection based on offset string. Also, our algorithm is mainly applied to planar specs. The purpose solution framework can be extended to the detection of weak surface self-intersection for specs. In the future of this plan, we are obtaining tailored equation back and analyze the gap that or
It's your turn. Yes, sorry. Yeah, I can back to you.
in 2021, we plan to end our presentation. Yeah. The same background, maybe the speed of the set in the data in lot of work of the for planar background and the planar compact is not is not going to be used in some and still doing the spot of the plan next changes. You go and switch not plane when they set profile of the get against use of the cell then six. This is how the profile is the spectrum the plane of the plane release spec in relation to the plane associated the profile. The plane is the plane in the particle that the the planar section and the planar profile is uh, what is the maximum degree of where the degree of quadratic cubic? What is the maximum degree that we have tried for finding these equations? So what maximum degree that the degree can be the sensor quadratic cubic. But yeah, the degree is not a constant. The degree of the degree then down is right. But the degree then involves the degree is not a match. And you know, but you can check the rules that as you increase the degree. How robust is that? Sorry. We can we can compare outcomes in the outcomes the same by the result is that you think I have one count which is even even has paper on local distributed section rules. It's significant losses. It's the same of the first and lots of things. Yeah. If the number of seven that is equal to seven, then I need this let's take a simple thing. First, about three quadratic subdivision. It's going to be plus this.
Thank you for an introduction. And in the talk, we present new curvature-bounded subdivision scheme. It improves over classic Cardinal-Clark subdivision, which I recall at the limit point has unbounded curvature. And moreover, the new scheme retains a quality of original quadratic attraction subdivision and does this with fewer pieces. So outline, as you see, we start with the classic stuff and move gently to the recent subdivision schemes. So Clark. It starts with any mesh. The faces can be multi-sided, no restrictions for position of irregular nodes. After first step, it is important for us, we get already quad mesh. A couple of more refinements, and visually we get like a smooth surface. What is important for us that actually already after one refinement of quad mesh, we get a structure so-called CNET. CNET, black marks for the valence 5 in this example, and brown colored is for valence 3. And such input is already sufficient for high-end schemes. And if we add yet another layer of quads to the CNET, what is important, we can produce without any additional step, just by conversion from B-spline form to the Bezier form. One shown green Bezier, bicubic Bezier ring. It is important for us testing the quality of new schemes, since it is important. The scheme itself might be good, but even also it's important transition from the regular part to multi-sided. So we consider subdivision surfaces as a sequence of contracting bicubic rings. Here you see this extended CNET. We produce one bicubic ring as before. Still no subdivision. That Clark is very simple. One new rule is only for the central regular point marked. Correct? I hope you see. So now again we apply conversion to the Bezier form. We get a new ring, and it is C2 connected to the initial. Since curvature of Clark at the limit point is unbounded, it is known that it is known how to make it bounded. We have to find new rules not only for the central point, but also for its neighbors. Okay, we do somehow this and apply same conversion. However, it is really a naive approach, since new ring is even not C0 connected with the previous one. It is a wrong, it is a now correct interpretation of traditional curvature bounded schemes. There are many of them. We start with the CNET, but no, still no conversion to Bezier form. Now we have refinement, black marks regular refinement. You see red the new rules, and here I hope you see cyan marks the area for the next refinement step. And only now we convert to Bezier form. You see shown on the left one sector of this entire arrangement. And note that now we have 4 times more pieces than in Clark case. And after next refinement, everything is okay. The rings are C2 connected. Now we turn to the new quadratic-attracted subdivision. It was introduced also at SPM conference 3 years ago in Genova. And what is really new, it is already has two components, so-called black D-net, looks like something like a net before, but at the center you see what you call attractive quadratic. Refinement. We refine all control points where you see there are 4 new red points. The rest are obtained by the standard refinement, regular refinement, and again, cyan marks the area for the next refinements. Similarly as before, now we convert to Bezier form. Layout is the same as for traditional curvature bounded scheme. And if we proceed further, again, new ring is C2 connected to the previous one. And important point is how we start this subdivision. If you look back, you may get an impression that we take the extended CNet and just throw away the central node. No, it is not so in practice. In our approach, we really take only CNet, apply regular refinement, no special rules, only regular refinement. You see brown new nodes, and here to better see. Get already this new for the to start our scheme initial DNet. And what is important that since this brown new nodes are obtained by the regular refinement, no special rules, the initial data is retained, and the new ring will be connected to the designers. Now, how quadratic comes into the game? It is really important but technical work. Now only very brief sketch. First, we take intermediate, the degree 5, so the guide of total degree 5. At the center, you see this quadrant. Later on, we switch from this intermediate guide to pi degree 5, since it gives us more freedom, which is really important to get a high quality. And all calculations are done in symbolic form. In our case, we use Maple. And right now, also symbolic calculation. We sample this guide, by degree 5 guide. Obtained data is transformed to B-spline form, and so we get this new B-spline control points. New rules for this that to the control nodes that we colored red. Quadratic, how we refine it? It is really very simple. It's just a shrinking. And what is important, it is somehow looks a bit weird, the structure from two pieces, but it gives us advantage that first it gives good, it is convenient structure for analyzing eigenspectrum of this subdivision scheme. Here you, this shown matrix, here are new data is expressed via initial data. And what is important, since quadratic refinement lives on its own, there we have white matrix. What it means, it is zero submatrix. And it is gives convenient block structure. And from this quadratic part, we get what is expected by the theory, the dominant eigenvalue 1, then subdominant twofold, and what is important, the next eigenvalue is squared subdominant eigenvalue. What is needed for curvature to scheme be curvature bounded? Just we calculate eigenvalues of the matrix D, and due to this, since maximum it is less than lambda squared, we have already bounded curvature. So now finally go to the new scheme. Since nothing new we can say on quadratic part, it is here not shown, and shown only one sector what is going on with the DNet. Here mark what we do. Input is the same as for quadratic-attraction subdivision uniform net. At some spots, we insert new nodes. Only at some spots. We obtain already non-uniform distribution of the nodes, and we are shown black. And for the magenta, we take the new rules. Then again, as before, conversion to Bezier form, and you see really spatial layout instead of 12 pieces in the one sector, we have only 5 pieces. And here comes another trick that brown circles mark the data that would be needed for next step. However, our input is uniform. So what we do, since we work not the global B-splines, but with the, how to say, B-spline jets, we transform this data to uniform form in such a way that we retain all second-order Hermite data. And so on. Now the question remains why we call it fast. Okay, so here you see 3 rings of the Quadratic subdivision. Here, first for the to recall, you see the structure. One sector has 12 pieces of Quadratic-Attraction subdivision. New one, only 5 sector. Yes. Now we take 2 rings. I hope you see that it's really sparsely out. But if I would continue, the overall picture would be very messy. So what we do now here, we show this only rings without detail, just as like a collection of L shapes in each ring. And now we produce this in sorry. And now we produce these three rings. In case, careful, in, just a bit back. In case of quadratic-attraction subdivision, we have, you see, 36 pieces per sector. Our new RS scheme produces more than twice fewer pieces. When you look at this picture, I think you're still thinking why it is fast. Maybe this picture is really illustrates better. Now we leave quartz in peace and produce 4 more rings, overall 7 rings, with new scheme. And I hope you hardly see the tiny hole that remains at the center. And note, it is, I can't say it is slow, it is good, but there is a clear, you see, hole. And actually, with the same amount of pieces, we do what is actually suitable for the as a final surface. Now, concluding remarks, how at the final stage in production was done earlier. Now, nowadays, you see the principle is the same. No doubt we use the computers developing the schemes. So we have also the additional options like curvature shadings and so on. Now, on this quadratic part, as an example, you see well-known monkey set configuration. On the left, in the middle, it is as was already briefly sketched. We get D-net, and inside quadratic part. When you see at the highlight lines the distribution, they are excellent. Now, what we do, we pull up the quadratic part and transform it to have a cup form. And final surface already with some clear bump in the original monkey saddle, but still highlight lines distribution is perfect. Is excellent. We play even more. We now take this cup and rotate. We get at the first glance really maybe crazy shape, but highlight the distribution again is excellent. And now we have to say romp even more. We do in the first 2 steps. At the bottom, the same as here, but we pull down this quadratic part and flip. In the next step, we pull it up and again flip to have the same form as in the as here. And what we produce, highlights are not shown, would be here in this slide, would be very messy, but you really see that we can really work, in some sense, control what is this quadratic part. And so, already concluding, so I would say this new fast Istanbul subdivision scheme retains really a high quality of the original quadratic-attraction subdivision. Let's call it Genoa, since it was 3 years ago. And what is important, that the quality is retained, but as you shown, considerably less of pieces. And our scheme benefits from what was developed in the for quadratic-attraction subdivision, and the real novel moments that we use non-uniform refinement of B-spline jets, and second, also novel, this, as I told briefly, localized interplay, uniform, non-uniform. That is the key of new subdivision scheme. So, thank you for attention. What? Yeah.
Is the when you move and easy it's like all easy, right?
Yes, it will like disappear or extremely small, but I haven't told our, how to say, we like, how to say, hybrid approach. It was in our earlier papers, but after some steps, we replace the whole with a really high quality finite cap. But why we have to look what becomes at the limit point, since it is at the limit point we have a bad quality. No doubt, this finite cap would also have bad quality. These matters are related.
So this how what is the
In case I correctly understood the question, we also prefer not this, how to say, entire subdivision, but as was asked, we concluded a high quality finite construction. But what is important is that anyway, to achieve high quality, a couple of rings of subdivision are needed, and the traditional schemes do not have a sufficient, do not produce sufficient quality. And another point that's that subdivision surfaces, why we want to do sufficient amount of rings, we are very convenient for isogeometric analysis. Finite schemes also we have constructed G2 refinable, but they are considerably more complicated. That's the point.